Hello, my name is Gianmario Scotti and I'm a guest researcher here at the Aalto University in Finland, and I'm working in the microfabrication group in the Micronova Research Center.
Hello, my name is Ville Matilainen. I work in Lappeenranta University of Technology as a doctoral student in laser materials processing laboratory. My specialty area is additive manufacturing.
Hello, my name is Petri Kanninen and I work here in the Aalto University Department of Chemistry and I study fuel cells.
My initial idea was to use laser additive manufacturing, and Ville is going to talk about LAM a little bit later. So I thought of using LAM to make microfuel cells, because we are doing research and this is a field that is still just beginning. So there is a lot of prototyping going on. But previously microfuel cells have been fabricated using a clean room and microfabrication techniques. So these are some of the microfuel cells that I have done previously in the Micronova clean room, and several articles have been published. These ones are made from silicon, which is a pretty conventional material for microfabrication. However, for fuel cells in general, and as we could see later on, also for microfuel cell, steel is a better material because it's much more robust and it's actually more conductive than silicon. So those are properties that are advantageous. And LAM is a method that allows for quick prototyping. These are the LAM manufactured microfuel cells that we have made. So there are three designs. There is this one. This is a 1 by 1 square centimeter. This one is a 2 by 1 square centimeters, and this one is 4 by 1 square centimeters. As you can see, the flow field is just a field of small rectangular pillars. And then we measure these microfuel cells in a measurement jig, and these jigs have also been done in a rapid way. They've been 3D printed from ABS plastic. So since we had three different sizes of microfuel cells, we also have three different sizes of jigs.
When Gianmario presented the idea about making the fuel cells out of additive manufacturing, of course we were thrilled and excited of trying to do it with so, and I'm going to tell a little bit about the technique itself. So basically it needs a 3D model made with a computer program, and the 3D model is then prepared for the additive manufacturing machine by slicing it into the layer size, in our case 20 micrometers, and the parts are built from the bottom to top, layer by layer. I have some examples here, some demo pieces made with additive manufacturing. For example, here you can see a micro heat exchanger with channels that are impossible to manufacture with any other method than the additive manufacturing. Then we have here this lattice structure, also impossible to make with any other conventional manufacturing techniques. And since the additive manufacturing can produce parts which are hollow, we decided to make a hollow nut because it's lighter than the one which is totally solid, but it's also quite nice. This is the additive manufacturing machine that we have in Lappeenranta University of Technology, and from here we can see the laser beam scanning the layer, the geometry of the one layer, as it goes over there, and soon the recoater will be doing a new layer of powder which again laser beam is scanning. This continues until the part is totally finished. Now the recoating is done. And the beam is scanning again the new layer. Here you can see the stainless steel powder material which was used when the fuel cells were built.
Hello and welcome to the physical chemistry laboratory where we actually measured these fuel cells that we manufactured. And you might ask, what is a fuel cell and why we do it and why in micro size? Here is a basic schematics of a fuel cell. It involves feeding a fuel, hydrogen, methanol, something which can be oxidized on the anode, and then air or oxygen on the cathode, which will then reduce. And this will produce only water as a product if we use hydrogen as fuel, so it's very clean. And it's also very efficient, since we are transforming the chemical energy directly to electrical energy without combustion in between. And we want to do this in micro size because we need to power portable devices, and we can't use these big clunky systems for that. We need to do things in very small size, which means that things that are inside the fuel cell need to be in micro or even nano sized. The gases that we need in the fuel cells are stored in these bottles where they are fed into the system over here, and we control the flow rate with mass flow controllers, so you can adjust the rate as you please from very small to very large values. And the fuel cell is controlled by this potentiostat here, so it is basically a device that allows you to control the current that goes through the fuel cell or the potential that you have in the fuel cell, and measure the other value. And by this equipment we could measure our steel microfuel cells, and here you can see a normal polarization curve. So it starts here where you have the open circuit voltage, which is close to 1 volt, and then when you reduce the voltage you increase the current that is flowing until we hit the maximum current here at low potentials, which is more than 1.2 amperes per square centimeter, which is basically the world record of microfuel cells.
So I hope we have captured your interest in our research. This research was published in the Journal of Power Sources. You will find the link in the description of this YouTube video. In this article, we describe the methodology, we describe the devices that we have produced, we describe the experiments, and we also mention and explain why this technique is really good for fast prototyping. And we publish our really exceptionally good results, which we think are world-class, or in fact record-breaking results for microfuel cells.